differentiation. 3.7 is there's almost nothing in this section. Higher derivatives. I'd say the only thing in this section is that it's legal, so it is legal. It's acceptable to try to differentiate derivatives. And you take successive derivatives, and those things are called higher derivatives. So you take a derivative of a derivative. You can take a derivative of a derivative of a derivative, right? As far as the function allows you to go. So really, there's nothing in this section other than some notation. Notation is this: if somebody writes f, we have f prime for the first derivative. You put more primes for however many derivatives you want. So if I have three primes here, then that means the third derivative, etc., etc. Okay, so nothing fancy. If you want to denote some large number or some sort of abstract number that hasn't been specified, one uses a parentheses and then the number inside. So if I have parentheses 100, that would mean the 100th derivative. So I don't have to write 100 primes, right? This is the kth derivative of f at x, right? Other notation, there's the Leibniz notation, d dx. Really, I think it would make most sense to write it like this, to put parentheses around it and then put a k there. Often what you'll see is dk, dx, dxk, something like that. Whoops, should be enough here. You'll see something like that. They both mean the same thing. These all mean the same thing. And if I use the big K, then just big. If I use the big D for differentiation, then this is the kth derivative. Okay. So there's nothing. That's about it. Those of you who've seen some physics know that if f is position, right? F is position along some linear track, then f prime, right, is the velocity, right? The instantaneous rate of change of position with respect to time. The second derivative would be the instantaneous rate of change of the velocity with respect to time, which is acceleration. Richka, do you have a question? You have a question?
So how far can you go in terms of how many primes you can take? Can you do a triple prime?
Yeah, you can go as far as you like, and each of those things would have some meaning. If you're thinking of a physical example, then each of those things would have some meaning, right? The third prime would be the instantaneous rate of change of the acceleration, right? Sometimes they give that a name, the jerk, right? The jerk. Right, you could have the instantaneous rate of change of the jerk, right? I don't know if there probably is a name for that as well, but etc. You can keep on going. Yeah, Alfred.
If you kept on going on and on, would you eventually reach zero?
Would you eventually reach zero? Well, what do people think about that? Do you eventually reach zero? Not for everything. Maybe for some functions, you're going to reach zero. For what functions would you reach zero eventually? Polynomials, right? Because each time you differentiate the polynomial, the degree goes down 1, right? And so, if the degree is n, after n times, you're going to reach 0, right? And in fact, if you do reach 0, what does that tell you? If you do after, suppose you have some function and you differentiate it n times and you reach 0. Well, who knows? But we will know soon enough. Yeah, Rachel.
When do you switch over from like the multiple primes to just like the little number?
It's sort of up to you. Yeah, I think people definitely don't do it for 2, right? And don't do it for 3 either. But maybe for 4 and above. But there's no rule about it. Yeah. Okay, so just to give you an example, or just to make you do some work here. G of t is t over t plus 5. Okay, and I'd like you to find I have the third derivative written in my notes. How about the second derivative? Let's find the second derivative, please. Okay. Who would like to give it a shot, or turn to somebody and say what you've done or what you're doing? Okay. So what's the first? Somebody tell me what to do to get the first. Somebody tell me what to do to get the first derivative. I take, what do I get? Sharon, how about you?
T plus 5 minus t over t plus 5.
Right? The bottom times the derivative of the top, minus the top times the derivative of the bottom, right, over the bottom squared. Right? So that gives us 5 over t plus 5 squared. Right? And then you take the second derivative. What do you get? Anybody? You could do it using the quotient rule, but it's probably easier to do it using the chain rule. Like you could say this is 5 t plus 5 to the negative 2, and then just use the chain rule on it. Right? So negative 10 t plus 5 to the negative 3 times the derivative of t plus 5, which is just 1. Okay. Right. Another one along the same lines. K of x is sine of. No, that's not interesting. Okay. Rather than do another example, which is basically the same sort of thing, let's do something a little bit more interesting. Suppose P of x is a degree 2 polynomial. And you know that P of 0 is 2, and that P prime of 0 is 4, and P double prime of 0 is negative 7. can you determine p? Can you tell me what the polynomial is? Tell me what the polynomial is. You actually have enough information to figure it out. Okay. Just take 2 minutes on this and see if you can say anything about the polynomial. P is a degree 2 polynomial. Okay, turn to somebody else then. If you haven't started talking already, start talking. Okay, so somebody tell me how to say something about this polynomial. And maybe you're going to keep on talking. I'm going to keep on talking. Okay, somebody tell me anything that you know about this polynomial. What do you know about this polynomial? Anything, Shravya? There's a plus 2 in there somewhere, right? Because the p at times 0 is 2, right? And you know that, what does your polynomial look like? It's a degree 2 polynomial, so it's got to look like ax squared plus bx plus c, right? It's a degree 2 polynomial. So what do you know about it? That the c is 2, right? Because when you evaluate it at times 0, you get 2, right? So we know that p of 0 is 2. Well, 2 is a 0 squared plus b 0 plus c, and so that tells you what c is. Right? C is 2. What else do you know?
B is 4.
B is 4. How do you know that?
Because if you take the derivative of
Right. So you take the first derivative of p here, right? You don't know what these numbers are, but you know that they are numbers, right? You don't know what A, B, and C are, but you know that they are constants. So you differentiate, you get 2ax plus b is p prime, and then you evaluate that as 0, and you see that b must be 4. So p prime at 0 is 4. That tells you that b equals 4. Okay, and then the last one, what's a?
-3.5.
negative 7 over 2. Right? So p double prime we see is 2a. Right? P double prime is 2a. At 0, of course, that's still 2a. And it's negative 7, so that tells you that a is negative 7 over 2. Right? Okay. So,
Sorry. Can you go over the P double prime?
yeah. Yeah. So we take this and we differentiate it to get this. We differentiate this to get this,
Yeah.
right? And then you say, what information do we have? We know that p double prime is negative 7, right? But p double prime at 0 is negative 7. But we know that p double prime is a constant, right? P double prime is a constant function, 2a. It's 2a throughout, right? So no matter what point we evaluate, at every point, and in particular at 0, we're going to get 2a. So that tells us that a must be, that gives us information about a. A has to be negative 7 over 2. Okay. So what this leads you towards is understanding that if you know the values of the function, if you know the values of the polynomial and all its derivatives at 0, then you know the polynomial exactly, right? So if you know these 3 bits of information about a degree 2 polynomial, then that determines your function. That determines your polynomial for all time, right? So all you need, right? You have some polynomial, right? But it's kind of interesting. All you need to know is the function, the polynomial's value here, and the value of the derivative here, and the value of the second derivative, the third derivative, fourth, right? And once you do, that determines the polynomial exactly, and that tells you the information throughout all time, right? That should be a little bit remarkable. Yeah.
Is that hard if it is a function like that though, where it crosses 0 a few times?
Why so?
Because there can be different values for. Oh wait, no. I was thinking y.
Okay. Yeah. So pretty cool, right? No, you're not going to have 2 polynomials. This information determines your polynomial exactly. Okay. So, any other questions about that? Okay. Okay. Actually, let me erase everything. Okay, 3.8. The method of implicit differentiation. How many of you have seen this before? Some of you? Okay, some of you have seen it before. Okay, so here's the idea. Let's give an example problem. So here is x squared plus y squared equals 4, the circle of radius 2. Okay. And here's a point on the circle, negative root 3, negative 1. Okay. And I'd like to know, what's the slope? Here's a simple question. What's the slope of the tangent line? Slope of the tangent line to the circle at that point. What's the slope of the tangent line to the circle at that point? Right? How do you figure it out? How do you figure it out? How do you figure out, Michelle?
You isolate y and find the derivative.
Okay, so you could say, I know that y squared equals 4 minus x squared. I know that y is going to be plus or minus root 4 minus x squared, right?
And then at that point, you have to plug in negative square root of 3 and with that in x.
Okay, so, right, so, right, that gives me the graph of the function. Actually, it gives me both parts of the graph, right? The upper part and the lower part. It gives me actually the graph of two functions, right? Which one do I want? Which function do I want? The lower one, right? I want f of x is negative root 4 minus x squared, right? And then how do I find the tangent vector, the tangent line?
Well, you could find the derivative.
Okay, find the derivative of that. Right? So f prime x then is going to be negative 1/2. Somebody tell me what to write, just as exercise. 4 minus x squared, negative 1/2.
Shouldn't the 1/2 in the front be positive? Oh, wait, just kidding.
Time minus 2x, right? Okay. So these guys cancel, that cancels, I get x over the square root of 4 minus x squared, right? That's the derivative, right? And then I would evaluate that where?
X.
At x, what's my x? Negative square root of 3, right? So f prime at negative square root of 3 is going to be negative square root of 3 over 1. Right? Oh, yeah, Diana.
Why is the 2x after you do the chain rule plus 2x instead of minus 2x?
It was minus 2x, but I canceled it with the minus sign up here. Sorry, I rushed it. I was, right? Questions? Richka, question? Richard Stravia, questions? Questions? No? Cynthia, you have a question? Yes?
So is this implicit differentiation?
No.
Okay, thank
No.
you. I was like, okay, maybe you can comment.
No. So this is the way you would do it. This is the way you would do it, using your current knowledge. Right? Yeah, this is the way you would do it using your current knowledge. So that, let's call this method 1. Yeah, you should be sort of disappointed if like, what? That looks like what we did before. It is what you did before. Okay, so method 2. Right, so method 1 was basically solve for y as a function of x, then differentiate. Okay. Method 2 will be assume that y is a function, or can be realized as a function of x. Then differentiate the expression. Okay. So here, what you differentiate is you solve for y, right? This f is really, maybe it's better to think of it as y, right? Y is a function of x, right? Right? You solve for y as a function of x, and then you differentiate y. Okay. Here you sort of from the beginning you say, well, look, I know that I'm going to say that my y depends on my y can be realized as a function. There's some function involved. There's some functional relation here. As the x changes, the y changes, right? There's an implicit function here, right? Y is implicitly a function of x. Okay, and so you realize, you say, well, y is actually a function of x. So I'm going to write this as, write the relation x squared y squared plus y squared equals 4. I'm going to write that as x squared plus this function of x squared, function y as a function of x squared equals 4. Okay, and then I'm going to differentiate not y. I'm not going to solve for y and differentiate, but I'm just going to differentiate the whole thing. Okay. I'll differentiate the whole thing because maybe it's not so easy to solve. If it's not so easy to solve for y, then this first method is not going to help you. Okay. So you differentiate the whole thing. So let's differentiate both sides with respect to x. Right? And you get, well, what's the derivative of x squared? 2x. What's the derivative of this function of x squared? 2y times the derivative of y. And the derivative of 4 is equal to 0. Everyone see that? Right? Okay. And so this gives us a relation between y prime, y, and x. Right? Gives us a relation between y prime, y, and x. It says that 2x plus 2y plus y prime at x is equal to 0. Okay. So in particular, right? So at root negative 3, root negative 3, negative 1, this says that negative 2 root 3 plus negative 2 y prime, right, equals 0. Right? In other words, y prime is going to be negative root 3. Right? You move this to the other side, right? And then you divide everything by 2, right? And you get y prime is negative root 3, which is what we got over here, right? Y prime at negative root 3. If you want, I'll keep the x in, right? At negative root 3 equals 0, and negative root 3. Okay, you see that you get the same thing. Somebody have a question? Yeah, Cynthia.
In terms of like notation,
Yeah.
I know you already use x in terms of x. So could we use like dy and dx?
Yeah, sure. That's fine.
Okay.
That's fine. That's fine. So if you use this instead of y prime, y prime x is the same thing as d dx y x, or this dy dx is sort of an abbreviation, but whatever. As long as you understand what you're doing. Leanna.
You plugged in negative 1 into the y-axis.
Yeah.
Right? Okay, just make sure.
Yeah, right. We know that 2, right? What do we know? We know that 2x plus 2y times y prime is equal to 0, right? So that tells us that, y prime is actually negative 2x, negative x over y, right? That gives us a relation. Y prime is negative x over y, and so at negative root 3, negative 1, we get negative root 3. We get root 3 over negative 1. Okay, so this is the second way, implicit differentiation. Which way do you like? Who likes the first way? Who likes the second way? Each way has its advantages. So there's no I'm not going to say you guys are wrong to like the first one, or you guys are wrong to like the second one. No, each way has its advantages. Okay. Okay. So. Okay. Let's have you guys do one. Negative 5x cubed equals x plus 2y over x minus y, and the point is negative 1, 2. So there's a graph. Here's an equation that describes a graph. Okay, and here's a point on the graph, and I'd like to know the equation of the tangent line. And you see that really method 1 would not be easy to, well, maybe you can still do it. But anyway, do it using implicit differentiation. Okay, and I'll hand back some homework while you guys are working. Not even here? What? That's not good.
I just put it on.
Okay, so who would like to say what they did? Or turn to somebody else and say what you're doing?
Well, I didn't finish it.
Okay.
There's no way.
Okay, so what do you do? Somebody tell me what to do. Taylor, you looked at me? Too bad. You looked at me? I'm going to ask you to do it.
Okay, so
Yes.
I changed, okay, so I put negative 5x cubed
Yeah.
equals x plus 2 2 times y of x.
So you change everything to,
Yeah.
change the y's to functions of x, yeah, and then,
And then I did the derivative
Okay.
of both sides.
okay, so what do you get on the left
So I
side?
get negative 15x squared.
Mhm.
And then the square I was.
Yeah, yeah,
the
so
base.
so what do you do? Oh, you were making a face, I see. I see.
Well, yeah, because I got a big, long, scary thing.
Okay, that's okay then.
Okay. So I have 2 minus y of x times 1 plus.
2 minus y of x.
Yeah.
2 minus y of x. Where do you get that 2 minus? Did you do it slower? Do it slower, please. So what do you do from? How do you differentiate
Oh,
this?
wait. Okay, hold on. I had.
So what rule do you use? here?
For when I was changing x and y, I wrote 2 minus y of x instead of x minus y of x.
Okay. Well, just tell me what rule. What do you want to do? How do you differentiate? The quotient rule, right? Okay. So you take the bottom times the derivative of the top. What's the derivative of the top?
1 plus 2. Wait, no.
2
2
y prime,
y prime.
right? Because you want to differentiate everything here with respect to x. You differentiate this with respect to x, you get 1. You differentiate this with respect to x, you get the derivative. Sort of a meaningless statement. You differentiate, you get the derivative. Right, so bottom times the derivative of the top minus the top times the derivative of the bottom. What's the derivative of the bottom? Taylor?
1 minus y prime.
Mm-hmm. Everything over the bottom squared. And so this gives you a relation, right? This gives you a relation between x, y, and y prime, right? And then you just plug in, right? You say, okay, x is negative 1, right? So let me write this a little bit more simply, right? X minus y, 1 minus 1 plus, 2y prime, minus x plus 2y, 1 minus y prime. People usually write this, sort of abbreviate it, x minus y squared. So people, leave out the dependence just to make it a bit cleaner. Okay, and then you just plug in, right? So you get that, x is negative 1, so we get negative 15 is equal to negative 1 minus 2, that's minus 3. 1 plus 2y prime, 1 plus 2y prime, minus x plus 2y, so that's 3. 1 minus y prime, right? Everything over x minus y squared, right? So that's 9 on the bottom, right? And so you end up with negative 3 minus 6y prime minus 3 plus 3y prime over 9 equals negative 15. In other words, negative 3y prime minus 6 over is 100, well, over 9 is negative 15, right? And then you solve for y prime. The rest I'm not going to do. It's arithmetic. Yeah, Emily.
Why does the y? Okay, so in P and P prime, the y values are all going to be different, right? The x values are the same, but all y values are different, right?
Say that again.
So when you compare P and P prime,
What's P prime?
What we're finding.
Y prime is what we're finding.
Oh, y prime. I thought we were using P still. Aren't we?
P is the point. So
Oh.
we have some
Okay.
graph, and we have some point. The point is negative 1, 2, and we're wondering the equation for the tangent line at that point.
Right. So why can you? Because it's exactly that point. Okay.
Yeah.
I remember.
Okay. Yeah. Yeah, Cynthia.
I have a question about the quotient rule.
About the what?
The quotient rule.
The quotient rule. Okay.
In general,
Yes.
because you do low d high minus high d low.
Yes, yes.
Over low squared. But I don't know, or is that the order, or does it
Yes.
not matter if you use, it does matter, right? If
Yes.
you use like high d low, it changes it.
Yes.
Okay, so it's low.
Yes. bottom, I don't know this song of yours, but bottom times the derivative of top minus top times the derivative of the bottom over the bottom square.
Thank you.
Yes, Rachel?
So with UNOPA, what I did when I was doing it is I ended up solving for y prime just because I thought that made more sense.
Yeah, sure, why not?
And then it looks nicer. And then
Yeah,
you can,
sure, why not?
simplify it.
Yeah. You get the same thing. Yeah. So if you like, you could at this point, multiply through and then solve for y prime, and then at the very end plug in, or you can plug in now and then solve, right? It's like there's two flights of stairs. There's two levels and stairs at both ends. You either walk down the hall and go up the stairs, or you walk up the stairs and then go down the hall, right? It's the same thing. Yes.
So is the purpose to do it to simplify that?
Yeah. Okay. So negative 1/3 y prime is equal to minus 2/3, negative 15, right? So you get minus 14 and a third equals negative 3/3. So you multiply both sides by 3, and you get negative, so you get 43, right? But that's arithmetic, so I sort of thought I didn't want to do it. You guys can do arithmetic. I'm lazy. Okay. So last, any other questions before I do one last trick? Okay. So the last trick is to use implicit differentiation to find higher derivatives. And you might imagine that this is just sort of a pain, and it's true. Okay, so here's the example. Xy minus y squared x equals x minus 1, and the point is negative 1, no, I'm sorry, just 1, 1. And the problem is to find the second derivative at that point. Okay. The second derivative at that point. Well, as you might imagine, it's just a matter of differentiating twice. Right? So you say, okay, we've got x minus y. I'm going to write this out. Expressing y as a function of x, and then I'm going to differentiate it. Right? Differentiate it. You get the first guy times the derivative of the second guy plus the derivative of the first guy times the second guy. Here you get I'm just going to write out what you get. Negative y squared minus 2y prime times x. Right? The first guy times the derivative of the second plus the derivative of the first guy plus the derivative of the first guy times the second, and you differentiate the right side, and we get 1. Okay. Okay. Now we also want information about the second derivative. So to get information about the second derivative, we need to take this expression and differentiate it again, right? So we get the first guy times the. Let me write this one in a cleaner way. Xy prime plus y minus y squared minus 2y prime x equals 1. Okay. I'm going to differentiate that with respect to x. You get the first guy times the derivative of the second plus the derivative of the first times the second. Here you just get y prime, here you get negative 2y prime, and here you get, it's going to be a pain, but let's take this as the first guy. The first guy times the derivative of the second, plus the derivative of the first guy, so that's going to be 2 times the first guy times the derivative of the second, plus the derivative of the first guy times the second. Right? First guy times the second, plus the derivative of the first guy times the second, equals 0. Okay, we did it. Okay, so you just differentiate this thing, and you get the second thing. Okay, whatever. It's it's long, but it's not difficult. Is it difficult? It's not difficult, right? You just differentiate. Alfred.
On the left side, on the very bottom, where did you get the minus y squared value from?
The first thing times the derivative of the second, right? Here's a product here, right? The first thing, y squared, minus the derivative of the second, which is 1, times the second derivative of the second, right? What's the derivative of y squared x? It's going to be the first guy times the derivative of the second, plus the derivative of the first guy times the second. Right? And there's a negative sign here, so you get negative sign. Okay? Okay. Some of you look kind of confused, but you should only be bemused. Right? This is simply so you just do it again, right? And then you get an expression relating, right, x, y, y prime, y double prime, right? Here you have you have an expression relating x, y, and y prime, right? You use the first one, use this at 1, 1 to get y prime, right? Then you know what y prime is. Okay, that gives you the y prime. So then you use the second one, use at 1, 1 with this information, right? With this information to figure out to get y double prime. Okay. So it's just a matter of substitution as before. So it's a hassle, but not at all more. It's not any more. It's not deeper by any means. Okay. It's just double the hassle.